So previously we had a quick digression about decomposition of the exterior algebra induced by an almost complex structure. Now let's come back to our story. Recall that the setup was that we have a Euclidean vector space V, that is a real vector space together with a scalar product, and we assume that V has finite dimension. We then ask the question about relationship between the scalar product on V and an almost complex structure on V. We then saw that in the case when V is of dimension 2, then they are almost the same thing. A scalar product on V uniquely determines an almost complex structure on V, and conversely, an almost complex structure on V uniquely determines a scalar product up to conformal equivalence. Then we saw that this no longer holds for V of arbitrary dimension. In that situation, a scalar product and a compatible almost complex structure I together uniquely determine a form called the fundamental form associated to I and the scalar product. And actually any two of these structures determine the remaining one. Now together they're gonna induce a Hermitian form on V. That's gonna be the subject of the next video. In this video, we just want to talk quickly about a property of this fundamental form omega. We claim that omega is real and of type 1, 1. What that means is that omega lies in this intersection. To see that, let us first quickly review the definition. So, omega of V, W is defined in terms of the scalar product and the almost complex structure I as follows. So that's gonna be I of V, and then scalar product with W. And observe that that's just the same as minus of V, IW. How do we see this? Well, just apply I to this. Because remember that the scalar product and I are compatible, so the scalar product doesn't change when we apply I to this. And I squared is just minus the identity. Alright, so that's the definition. Now, let's see why this holds. First, let us check that omega lie in this wedge 2 of V dual. In other words, we need to check that omega is alternating. So let's look at omega V, W and let's try to show that it's minus of omega W, V. By definition, this is just a scalar product of I of V with W. Whereas this bottom term here is equal to minus of IW, V. And we can immediately see why these and these are equal, because both of them are equal to minus of V, IW. Here again, we get from the first step to this second step by applying I. And from this second step to this third step, we're just using the symmetry of the scalar product. Alright, so this shows that omega is alternating, and so it must lie inside this space. Now, let's check that omega lies inside this space. We claim that it suffices to show that this I omega is going to be equal to omega, where remember for any vector space with an almost complex structure, this map I is defined to be the multiplicative extension of the almost complex structure. In our specific situation here, I can be given by the following formula. This is because omega, as we have established, is an alternating form. So it lies in this space and we have the following decomposition. Using the definition of I, we get the following decomposition of I omega. Now if this is equal to omega, then that means that this component to 0 component are equal. And then this part must also be equal. Sorry, I made a typo here. This should be 0, 2. But this would mean that this 2, 0 component must be 0, and so is this component. And thus omega only has the 1, 1 component, so omega must be of type 1, 1. Alright, so let us show that I omega is actually equal to omega. Let's apply I omega to some pair of vectors, V and W. Then we have established in the previous video that this is just equal to omega applied to I of V and I of W. But these, boldface I applying to V is just I of V. where this I here was the almost complex structure on our vector space. Because remember, this boldface I was just the extension, the multiplicative extension of this I. And now this, by definition of omega, is just gonna be I, the scalar product of IV with IW. Now since I square is minus identity, this is just scalar product of minus V with IW. And we have established that that's just omega of V with W. So indeed, I of omega is just omega. This then implies that omega is of type 1, 1. And thus we have established that omega must lie in this intersection. Up next, we're gonna talk about the Hermitian form induced by omega, the scalar product, and the almost complex structure.